Hi, my name is Wojciech, and it's my pleasure to talk to you today about the recoverable consensus hierarchy. This is the outline of my talk. I'm going to first motivate the problem and connect it to persistent memory. And then I'm going to define recoverable consensus, describe some transformations that solve it, then present some impossibility results, and finish with my concluding remarks. Let's start with the motivation and background. The fundamental research question addressed in his work is the following. What happens to shared memory algorithms when we allow processes to transition spontaneously back to their initial state? In this context, back to their initial state means that the program counter is reset to the first line of the algorithm followed by a process, and any private variables of that process are reset to their initial values. It is known that weight-free synchronization remains possible in this failure model, and this was shown in a 2015 Opodis paper by Berryhill, Golab, and Triponetara. The same paper shows that consensus remains universal for constructing weight-free implementations, but it doesn't say much about the computability of consensus itself. This work finds motivation in the recent commercial release of persistent main memory, which allows shared memory algorithms to store state in such a way that it can survive both process failures and system-wide failures. Let me explain how a system with persistent main memory would respond to different types of failures. Case 1 is a system-wide failure, such as due to a power loss, which is equivalent to a cold boot. Imagine that a program writes a variable x, and then another variable y, and then a third variable z, and it does not immediately flush these variables to the persistent memory. It is possible that, for example, due to cache evictions, some of these variables are spontaneously flushed, such as x and z, but the third variable y remains in the volatile cache. If a system-wide failure occurs at this point in time, the new values of x and z remain in the persistent memory, but the new value of y is lost. This outcome poses two problems. Number one, the state of persistent memory reflects an incomplete execution of this algorithm. And number two, the particular state is inconsistent with program order. The latter problem can be solved by adding flush instructions and store fences to this code, but the former problem is more fundamental. Case 2 illustrates what happens when an individual process fails, for example, due to a seg fault. Suppose that we have the same program as in case 1. A process writes x, then y, and then z. It's possible that x and z are spontaneously flushed to the persistent memory, and then a crash occurs, but in this case, because it's a software failure and not a hardware failure, the new value of y remains in the volatile cache. In other words, it is not lost from the memory hierarchy. Let's pause and ask the following fundamental question. In the scenario just shown, did we lose anything important? In other words, is there something stopping us from resuming execution of the algorithm exactly from the state it had at the time of failure? The answer is yes, and the reason is that a lot of important state is stored using CPU registers. These registers store states such as the program counter, stack pointer, as well as the values of certain program variables. CPU registers are volatile, which means that they cannot survive a system-wide failure, but this is not quite relevant to our example, which is based on an individual process failure. The more relevant observation is that when a process fails and its program is restarted, which creates a new process, the old process and the new process might run on different cores and use completely different sets of registers, and therefore there's no continuity in terms of the values stored in those CPU registers before the failure versus after the failure. Let me give you another example. Consider the following two-process leader election algorithm where symmetry is broken by applying a test and set operation on a shared object T. When this algorithm is compiled to binary code, it looks more like this, where the first statement is now split into two statements. One line calls test and set and saves the response in the CPU register, and another line uses the value of that CPU register to evaluate the branch condition. If a crash occurs between these two statements, we cannot simply resume execution at the if statement because we no longer have the value of the CPU register from before the crash. We might be tempted to go back one step and re-execute the test and set operation in order to populate the CPU register with a value. However, in this example of leader election, that would lead to a loss of safety. Our discussion leads to the following insight. In both failure models, which means individual and system-wide failures, the potential loss of the response from a read-modify-write operation complicates the design of recoverable algorithms. In other words, we are more concerned with the return values of read-modify-write operations than we are with the persistence of the main memory itself. Bearing that insight in mind, here are the abstract modeling assumptions. There are n asynchronous processes, and these processes are subject to crash recover failures, by which the processes forget the values of their private variables and revert to their initial state. Such failures can be system-wide, which means they affect all processes together, or independent. Processes communicate using shared memory, which supports atomic read-write and read-modify-write operations. The state in shared memory survives failures, but the responses of memory operations are captured in private variables, which do not survive failures. I don't say anything about the volatile cache or about flush instructions. In fact, for simplicity, I assume that there is no volatile cache and that flush instructions are not required. The simplifying assumption is removed easily by inserting flush instructions and additional store fences. And this is exactly what you would do if you wanted to take the algorithms presented in this work and make them run on a real-world multiprocessor with persistent memory. And as far as impossibility results are concerned, there's no need to remove the simplifying assumption because it actually makes our results stronger. Let's proceed with the contributions. First, I'm going to define recoverable consensus. In the consensus problem, processes propose potentially different values and they have to agree on a single value. For conventional consensus, agreement states that two processes cannot output different decisions. But for recoverable consensus, we have to broaden this definition because one process may execute the consensus algorithm multiple times. On the other hand, the validity property is unchanged. It states that each decision returned is the proposal value of some process. Finally, for liveness, we have recoverable wait freedom, which in the context of consensus states that each time a process executes its algorithm from the beginning, it either returns a decision after a finite number of its own steps or crashes. When analyzing the correctness of a recoverable consensus algorithm, we can ignore the circled part at the top, which talks about one process returning different decisions in distinct executions of the algorithm. The reason we can do that is because the same algorithm, presuming that it's valid and recoverably wait-free, will also allow two distinct processes to return different decisions. This claim is straightforward to prove, and proof sketch is illustrated in the top right corner of the slide. Suppose that one process P outputs different decisions D and D prime. All we have to do is wake up a second process Q, wait until it outputs a decision D double prime, and then we are guaranteed that Q disagrees with at least one of P's decisions. We can discuss the computability of recoverable consensus in terms of consensus numbers, similarly to conventional consensus, and these are defined in the usual way. For any shared object type T, the consensus number of T with respect to a given failure model is the maximum number M such that a finite number of objects of type T and a finite number of additional read-write registers can be used to solve consensus or recoverable consensus in our model for M processes, but not for M plus 1 processes. Because there are multiple consensus hierarchies, I define some notation in the paper to separate their consensus numbers. M-HC refers to type having consensus number M in Hurley-Heath conventional consensus hierarchy. M-RC-S refers to consensus number M for recoverable consensus with simultaneous failures, and M-RC-I refers to consensus number M for recoverable consensus under independent failures. With that notation in mind, this is what the conventional consensus hierarchy looks like. CAS is universal, it has infinite consensus number. Read-write registers have consensus number 1, and several important types have consensus number 2. With respect to recoverable consensus, we can make a number of general statements relating consensus numbers. The consensus number of a primitive in Hurley-Hees consensus hierarchy is greater than or equal to the consensus number in the recoverable consensus hierarchy with independent failures and the hierarchy with simultaneous failures. And similarly, the consensus number in the hierarchy with simultaneous failures is greater than or equal to the consensus number in the hierarchy with independent failures. Next, I'm going to present some transformations that solve recoverable consensus using conventional consensus as a building block. The first transformation is for system-wide failures, and it uses two-process conventional consensus to solve two-process recoverable consensus. In other words, this transformation proves that 2HC implies 2RC-S. Since the converse follows easily, we conclude that in fact 2HC is equivalent to 2RC-S. The transformation is fairly simple. It uses a two-element array to store proposal values, a single conventional weight-free two-process consensus algorithm C, and a shared variable D to store the decision computed using C. And here's the transformation. The flow of control is as follows. A process will, in the absence of failures, save its proposal value to the shared array P, then compute a decision using C, and record that decision using the shared variable D. Recovery proceeds by case analysis. If neither process has written its proposal to the array P, then we proceed to lines 3, 4, and 5 as in the failure-free case. This is the only case where we are guaranteed that no process has started executing C, and therefore it's the only case where it is safe to attempt to access C after the failure. If some process already saved its proposal to P, then we check D. If D holds the decision value, then we return that value at line 8. Otherwise, we proceed with a case analysis where the proposal of one of the two processes is chosen as the decision value. This algorithm is specific to the case of n equals 2, and there's no obvious way to generalize it to a larger number of processes. The second transformation presented in the paper is for independent failures, and it assumes that the number of such failures is bounded from above by a constant f. This transformation can be used to show that any primitive at level 2 in the Hurley-Hees hierarchy remains at level 2 of the recoverable hierarchy in this particular failure model. This transformation does not show that such a primitive is 2RC-I because of the restriction on the number of failures. The transformation actually transforms n-process conventional consensus to n-process recoverable consensus. To do so, it uses f+1 instances of the conventional n-process consensus, as well as an array R of read-write registers and an array D of read-write registers. Roughly speaking, this transformation attempts to get processes to agree using C0. If this is not possible because of a failure, then it attempts to use C1 and then C2 and so forth up to CF. Making this idea work correctly is challenging because we have to deal with independent failures. Consider, for example, the scenario shown in the top right corner of the slide. Process P reaches a decision using C0. Process Q attempts to do the same but fails, and then has to move on to C1 because it is not safe to go back to C0. Thus, P reaches a decision using C0, Q reaches a decision using C1. Those are potentially different decisions unless we synchronize them using the additional shared variables like the arrays R and D. Here is the full algorithm, which is structured as a for loop. And inside this for loop, we iterate over the different instances of the conventional n-process consensus. Process PI uses RI to remember which consensus algorithm it was attempting to use prior to its most recent failure. We can think of this value as a monotonically increasing counter. The next conventional consensus algorithm identified by this counter is accessed at line 21, and then the decision is stored using the array D at line 22. Before reaching line 21, we have to first check if anyone already reached the decision in a lower numbered iteration. And this is done at lines 18 to 20 by iterating over the elements of the array D. If a decision is discovered for a lower numbered iteration, then at line 20, process PI replaces its own proposal with that decision. This part of the algorithm synchronizes PI with either itself or another process that may have reached a decision in an earlier iteration. However, while PI was executing lines 21 and 22, another process might have already failed and advanced to the next iteration, and so we also have to synchronize PI with any process that may have already reached a decision in the higher number iteration, and this is done after line 22. The mechanism at lines 23 to 26 is to check the entries of the array R belonging to other processes and see if anyone has already advanced to a higher iteration than the iteration K executed by PI. If such a process PZ is identified, then at line 26, PI forgets the decision value it computed earlier at line 21 because it may not be safe to use this value. Instead, it will allow the main for loop to continue to the next iteration, K plus 1. Having synchronized properly with both earlier iterations and later iterations, process PI reaches line 27 and checks whether it still has a decision. If it does, then it returns that decision at line 28, otherwise it will proceed to the next iteration and try again. The assumption that the total number of independent failures is bounded by the constant f ensures that process PI executes line 26 at most f times. Because the outer for loop has up to f plus 1 iterations, this ensures that eventually PI executes an iteration where it does not execute line 26 and does return a decision at line 28. As explained later on, the use of exactly f plus 1 instances of conventional consensus in this transformation turns out to be optimal. Aside from the transformations, the paper also presents some impossibility results. The paper proves two impossibility results in the model with independent failures. Result 1 is a space-bound for test and set based recoverable consensus algorithms, and it states that if there are up to f failures, then f plus 1 instances of tasks are necessary, and this proves the optimality of the second transformation presented earlier in this talk. The second result concerns consensus number, and it states that if there are arbitrarily many failures, then recoverable consensus is not solvable using test and set, fetch and store, or fetch and add, even if we are given infinitely many such objects. The second result implies that several primitives at level 2 in Hurley-Heath hierarchy drop to level 1 in the recoverable hierarchy with independent failures. This separates the recoverable hierarchy with independent failures from both the conventional consensus hierarchy and from the recoverable hierarchy with simultaneous failures, where these primitives were shown to be 2 RC-S. Both impossibility results are proved using roughly the same technique, which is valency-based and which is inspired by Hurley-Heath's analysis of the conventional consensus hierarchy. The proof adopts Hurley-Heath's definitions of V-potent, V-valent, univalent, and bivalent states. Hurley-Heath's technique does not work out of the box for us, and it has to be adapted in a couple of ways. First of all, we have to deal with the possibility that if a process continues to take steps, it may never reach a univalent state for the simple reason that it may crash infinitely often and not make any progress. We also have to deal with a larger number of state transitions. For example, in a deterministic two-process algorithm, there could be 4 transitions out of a particular state, and even if processes P1 and P2 are both enabled to take decision steps leading to univalent states, it is possible that both of those decision steps lead to the same valency rather than to opposite valencies as required in Hurley-Heath's proof. Both technicalities are avoided by restricting our attention to a particular subset of execution histories where only one designated process PI is permitted to fail, and if this process fails f times, then the other process PJ has taken at least f steps failure-free. This technique is reminiscent of pruned computation trees, which were introduced by Lowe and Hatzidakos, and is also similar to a proof developed in parallel by Atiyah, Ben Baruch, and Handler. The latter was published in POTC 2018 in parallel with an earlier draft of this work. The main challenge in using this proof technique is to construct the usual execution history leading to a contradiction in a manner that preserves invariant number 2. I'm out of time to explain this in the presentation, but I invite you to read the details in the paper. To prove the spacebound, which is our first impossibility result, we introduce another restriction on execution histories. Process PI may fail if and only if its previous step was its first access to some test and set object in the execution history. This restriction ties the number of failures by PI to the number of test and set objects used. Conclusion. I presented the recoverable consensus hierarchy and showed you that it looks a little different than the conventional consensus hierarchy. I also separated the model with independent failures from the model with simultaneous failures in terms of the computability of recoverable consensus. Thanks for watching this video. If you have any questions, please find me on Slack during the conference or contact me using the email address shown on the title slide of this presentation.